Good morning, sir. Today we are going to present our communication and computer network group project. So we have 6 group members, which is me, Liang Chi Kyung, Chong Ren Zhen, Michael Hugh Zhen Yong, Kwan Pei Yi, and Jasper Ling Biao. So we will start our presentation with introduce of ARQ. So first is the stop and wait ARQ. Stop and wait ARQ is one of the communication techniques that used to transmit data between two linked devices. The flow of this ARQ is: first, sender A send a data frame or packet with an assigned sequence number and wait for acknowledgement, which is ACK, from receiver before transmitting the next one. A timer is start for this packet. Then receiver B, after receiving the data frame, send an acknowledgement with an assigned sequence number. Then sender A, which received the ACK for previous send packet that within certain period time, and it will transmit the next packet. If the sender didn't receive an ACK within the certain time period, it is considered the packet was lost or corrupted and retransmit the packet again.
ARQ protocol, go back N. Go back N uses a sliding window to send multiple frames up to a specific window size without waiting for individual acknowledgement. The receiver only acknowledges the last correctly received in order frame. Out of order frames are discarded. If a frame is lost or an error is detected, the sender goes back and retransmits that frame and all subsequent frames, even if some were received correctly.
ARQ protocol, selective repeat. Selective repeat is a type of automatic repeat request protocol used in reliable data transmission. The sender can transmit multiple packets based on a window size without waiting for individual ACKs. The receiver acknowledges each packet individually. Only the packets that are lost or corrupted that are retransmitted, not the whole window. Unlike go back N, the receiver buffer out of auto packets on until missing ones arrive.
So now we will go to our experimental setup. To conduct the simulation of network condition for each test cases, we have set the increment and decrement for the parameters, which is packet loss probability, ACK loss probability, bandwidth, network latency, timeout interval, and window size. For scenario 1, low packet loss and high bandwidth, we have set the decrement of packet loss probability from 0.18 to 0. The other parameters remain default. For scenario 2, which is high packet loss, low bandwidth, we set the decrement of bandwidth from 90 to 1. The others parameter remain default. For scenario 3, which is high latency with different timeout intervals, we set the network latency as 100 ms and the increment of timeout interval from 50 ms to 500 ms. For window size, we have two different sets of value. For selective repeat ARQ, we have set the window size as 8, 16, 32, and 64. For go back N, we have set the window size as 10, 20, 40, and 80. Continue with the experimental setup. So the default value for each parameter are preset in the simulation program. This is as shown as below. And the key performance that we recorded is throughput, total transmission time, bandwidth utilization, processing overhead, and retransmission count. Microsoft Excel is used to generate charts for analysis. Formula for calculate the bandwidth utilization is throughput over bandwidth times 100%. And formula for calculate the processing overhead is packet retransmission divided by total packet transmitted times 100%. So now we will go for the result overview for stop and wait ARQ, which is scenario 1, low packet loss, high bandwidth. And this is the second scenario, which is high packet loss, low bandwidth. The third scenario, high latency with different timeout intervals, and the impact of network latency for stop and wait ARQ. So we will continue with go backend ARQ. The result overview for scenario 1, low packet loss, high bandwidth. Scenario 2, high packet loss, low bandwidth. Scenario 3, high latency with different timeout intervals. Scenario 4, varying window size and impact of network latency for go backend ARQ. Also continue with selective repeat ARQ. Scenario 1, low packet loss, high bandwidth. Scenario 2, high packet loss, low bandwidth. Scenario 3, high network latency with different timeout intervals. And Scenario 4, varying window size. And the last one is impact of network latency for selective ARQ. After reviewing all the results, we now come to the analysis and discussion. So we will discuss for the first parameter, which is packet loss probability. For stop and wait protocol, as illustrated in the first chart, packet loss probability affects the number of packet retransmitted and efficiency of transmission significantly. When the probability is high, which is 0.18, the packet retransmitted is 41, while the probability drops to 0, the packet retransmitted is 13. This affects the value of processing overhead and transmission time, which higher probability will have higher value for processing overhead and transmission times compared to the low probability. The data for the processing overhead is from 29.1, nearly 29.1 drop to 11.5, while the transmission times is from nearly 0.1 second increase to nearly 0.99 second. The throughput also in the trend of increase while packet loss probability decrease. Lower packet loss enhance protocol efficiency by reducing retransmission delays and improve the data flow. For go backend protocol, from the chart, when the packet loss probability decrease, the total packet retransmitted also decrease significantly, which is from 36 to 17. Due to the go backend behavior, although the probability drops to 0, it still causes multiple retransmission. Throughput increased slightly from 1.69 Mbps to 3.32 MB per second because it presents entire windows, which affects throughput. Total retransmission time show trends of decreases caused by lower packet loss, reduced delay. Continue to selective repeat protocol. As packet loss probability decreased from 0.18 to 0, the throughput increased from 65.07 Mbps to 155.91 Mbps, and bandwidth utilization improved from 69.07% to 115.91%. Meanwhile, the total packet retransmitted dropped to 32 to 15, and the processing overhead decreased from 24.24 to 13.04%. The total transmission time improves from 0.01254 second to 0.0088 second. These results show that under ideal network condition, which is low packet loss and high bandwidth, selective repeat ARQ perform highly efficiently, delivering maximum throughput with minimal retransmission and delays. To summarize, selective repeat protocol have the best performance, which selective retransmission minimize redundancy, making it highly effective in high bandwidth, low loss environments.
Analysis and discussion on bandwidth. Stop and wait protocol. As seen in chart 2, different bandwidth will affect the most is the total transmission time with obvious change of its performance metric. When the bandwidth is 90 MB per second, the total transmission time is around 0.12 seconds, while the bandwidth dropped to 1 MB per second. the total transmission time is 1.7 seconds, and the transmission time becomes bigger when the bandwidth is smaller. However, the change in throughput and bandwidth utilization is considered small due to protocol behaviors: sends one packet at a time and waits for an acknowledgement before sending the next. This causes the sender to remain idle during the round trip time, which is RTT, which wastes available bandwidth. As for the go-back-N protocol, from the observed data, total transmission time have a significant change of value compared to other performance metrics, while bandwidth changes. At 90 megabytes per second, the transmission time is around 0.0057 seconds, while at 1 megabyte per second, the transmission time is around 0.015 seconds. Throughput and bandwidth utilization have a minor change, and it still depends on SCK. The sender cannot fully utilize the available bandwidth because it must wait for SCKs. If RTT is high, the sender sits idle, wasting bandwidth capacity. As for the selective repeat protocol, as network bandwidth decreases from 90 megabytes per second to 1 megabyte per second, the throughput also drops sharply from 63.37 megabytes per second to 1.15 megabytes per second. Then the total transmission time increases significantly from 0.0108 seconds to 0.7018 seconds. Bandwidth utilization climbs from 70.41% to 115%, surpassing 100% at low bandwidths due to excessive retransmissions. Despite the lower link speed, total packets retransmitted remains high, between 27 and 35 packets, and processing overhead stays relatively constant around 24.81%, indicating that no impact when bandwidth changes. This shows that under poor network conditions, selective repeat ARQ struggles to maintain efficient throughput, and this cost in time and overhead rises drastically as bandwidth shrinks. There is no doubt that the selective repeat protocol have the highest performance compared to stop and wait protocol and go back N protocol. Analysis and discussion on network latency. For the stop and wait protocol, high latency significantly degrades the performance of stop and wait protocol. On the chart 3, high latency, it's clearly shown that the transmission time have a significant increase compared to chart 1 and chart 2. As the protocol sends one packet at a time and waits for acknowledgement, increased delay causes idle periods, reducing throughput and utilization. The sender is forced to wait longer between packet transmissions due to the high network latency, which directly reduces throughput and increases total communication time. As for the go-back-N protocol, as network latency increases from 10 milliseconds to 90 milliseconds, the total transmission time increases significantly, and the higher latency causes longer delays in receiving SCKs, means longer idle times and slower progression through the transmission window. The value of throughput and bandwidth utilization almost remains at zero as latency increases. This is because it relies on acknowledgements before sliding the window forward. Packet retransmission count stays relatively high due to it is triggered by packet loss, not delay. As for the selective repeat protocol, as latency increases from 10 milliseconds to 100 milliseconds, the throughput drops significantly from 1.37 megabyte per second to 0.15 megabyte per second, and bandwidth utilization follows the same trend, decreasing from 1.37% to 0.15%. Meanwhile, the total transmission time rises sharply from 0.58696 seconds to 1.5066 seconds, indicating the substantial delays in data delivery due to the longer round-trip times. Despite these performance degradations, the total packet retransmitted remains high, and the processing overhead remains fairly stable, around 23%, suggesting that the protocol handles retransmission consistently but is heavily impacted by the delay in acknowledgements. This highlights that higher latency severely limits the effectiveness of selective repeat ARQ, reducing throughput and increasing overall communication time.
Analysis and discussion for timeout interval. For start and rewind protocol, timeout interval play a crucial role under high latency conditions. As seen in graph 3, when timeout interval increases, the transmission time also increases obviously. This is caused by the system had to wait for a long period to detect the possibility of lost packet, causing lower throughput due to idle waiting time. It is shown in the chart where the value of throughput and battery utilization are very small. Next is go back-end protocol. The graph illustrates how the go back-end protocol performs under high latency conditions when the timeout interval is varied from 50 to 500 ms. Retransmission range from 48 to 33 packets. Under high latency conditions, setting the timeout interval too long leads to excessive and unnecessary retransmissions, when setting it too high can reduce responsiveness and efficiency. This concludes that in high latency environments, calibrating timeout settings is critical to maintain both performance and efficiency in reliable data transmission. Last is selective repeat protocol. With timeout interval ranging from 50 ms to 500 ms, throughputs rate around 25 to 40 Mbps, while total packet retransmission range between 25 and 40. Processing overhead fluctuates between 20% and 28.57%, peaking at 28.57% for timeout of 300 ms and 400 ms. The total transmission time varies slightly, from 5.006 seconds to 6.5078 seconds, indicate the extremely short or long timeout can increase retransmissions or idle waiting. An optimal balance minimizes overheat when maintaining stable throughput, provide the importance of turning timeout intervals under high latency conditions. Analysis and discussion for window size. First is go back-end protocol. The number of retransmission packets fluctuates slightly across window size. The window size 10 and 40 shows the lowest retransmissions, indicate more efficient transmissions. The higher retransmission occurs at window size 20. Overheat is higher at window size 10, which is 9%, and lowest at window size 80. Smaller window size induce higher processing overheat due to frequency exceeds and retransmission handling. The go back-end protocol benefits from moderate window size, particularly window size 40, which provides a good trade-off between efficiency, raw transmissions, overheat, and performance throughput utilization. Increasing the window size improves throughput to a point, but it uses higher delays and resource overheats, making extremely large window less beneficial in particular applications. Next is selective repeat protocol. As the window size increases from 8 to 64, the throughput improves steadily from 85.54 Mbps to 95.82 Mbps, and bandwidth utilization rises in parallel, indicate better use of available network capacity. The total transmission time slightly decreases from 0.00968 seconds to 0.00814 seconds, showing faster data delivery as more packets are sent in parallel. However, the total packet retransmission time also increases from 31 to 35, and the processing overhead grows from 23.66% to 25.93%. This suggests a trade-off. When larger window size enhance throughput and efficiency, they may slightly increase retransmissions and CPU workload. Overall, increased window size benefits performance especially in high bandwidth or high latency networks, where walk-in requests can keep the pipeline full.
So we come up with the conclusion part, which is the performance of ARQ protocols varies significantly depending on network condition. For high packet loss low bandwidth, selective repeat perform best as it only retransmit erroneous frames, preserving bandwidth even in lossy condition. For low packet loss and high bandwidth, selective repeat offers the highest efficiency, fully utilizing bandwidth with minimal redundancy. Under high latency condition, selective repeat is ideal as it maximizes transmission during latency periods and avoid unnecessary retransmissions. For large window size with some loss, selective repeat excels by using the large window to keep throughput high and retransmitting only what's necessary. In summary, stop and wait is suitable for simple, low speed, low loss networks. Go backends balance simplicity and performance in moderately reliable conditions, while selective repeats offers the best performance across most scenarios, especially in high bandwidth, high latency, or loosely environment at the cost of added complexity.
This presentation about network design proposal for NAMI SDN PhD. This is for our course TMF 1254 is communication and computer network. Our group member is Chung Eun-jung, Young Ji-kyung, Hugh Jong-young, Jasper Lim Min-young, myself, and Kwang Pei-yi. For the introduction and project objective. The objective is design a cost-effective practical network for NAMI SDN PhD. The key requirement is single internet gateway, full office on different levels, stationary and mobile employees, network printers, and guest Wi-Fi in meeting rooms. The network requirement summary is for office air, there is level 1. The stationary employee is 15, mobile employee is 5, printer is 2, guest Wi-Fi is needed. And for office B, that is level 2. The stationary employee is 10, mobile employee is 3, printers is 1, and guest Wi-Fi is also needed. This is the network topology diagram. The internet that is connected to the modem, and the modem is connected to a firewall router. The firewall router is connected to the PLN. The T is for the guest. And firewall also connect to the level 3 switch that is connected to office A, that is level 1, office B, level 2. This is a cable that is connected to the PLN 20 for office A. Is connected to the printer and PC. This level 3 switch is also connected to the Wi-Fi router. It is also connected to the PLAN 10. And for Office B level 2 is connected to the PLAN 20 and it is connected to the PC and printer. For the inter-office connectivity, we prefer CAT6 internet or fiber optic because it is reliable and it is also high performance. It can easily handle internal traffic like sharing the file and printing stuff. Alternative wireless. This is only needed if physical wiring is impracticable.
And I will be presenting the second half of our proposal, covering slides 6 to 10, which include the network components, VLAN segmentation, switch planning, and our conclusion. Network components and technologies. This slide explains the core components and technologies used in our network design. First, the gateway, which consists of a firewall and router, provides centralized internet access and security control. For inter-office communication, we use Ethernet or fiber for high speed and stable connectivity. All stationary workstations are connected using Ethernet cables to ensure reliable connection. Mobile user will connect using Wi-Fi 6 access point, offering fast and secure wireless performance. Web access is separate using VLANs and separate IP to ensure their traffic doesn't interfere with internal system. Finally, our printers are IP network, allowing your user from both flows to print easily. VLAN segmentation strategy to improve security and manage traffic efficiently. We apply VLAN segmentation. We have 3 VLANs, one for the staff network, which isolates employee devices for internal use, one for guest Wi-Fi, which ensure visitors are securely separate from the main network, and one for printers to allow shared access without exposing other devices. This setup increases both security and performance of the networks. Capacity planning switch requirement. Here we show the switch planning based on the number of devices in each office. Office A has 15 PC, 5 mobile users, 2 printers and 2 access points. So a 24-port switch is selected. Office B has fewer devices, so a 16-port switch is sufficient. This switch also allows for future expansion, providing room for additional devices later on. In conclusion, our proposed design is both reliable and cost-effective. It meets NAMI Sendirian Berhad current requirements and is scalable for future growth. The network is also secure and manageable thanks to VLANs, modern wireless technology, and well-planned wire structure. That brings me to the end of my part. Thank you for listening.